Hello friends, welcome back to the tetrahedron chemistry classes. So guys, in the last class, I have introduced the uses of the polymers, right? And then I have explained the detailed classification of the polymers and the terminology, which is very, very important in order to understand the chemistry of the polymerization. These things I have discussed in my first lecture, okay? And in my today's lecture, which is the second of the series, I am going to discuss the mechanism of the addition polymerization in the detail, right? And if you are new here and you are watching video for the first time, so it is my advice that you can go through the first lecture as well. I am giving you the link in the description box. And if you are watching this video first time, you are new here, please subscribe the tetrahedron chemistry classes and do share with your friends also. Okay, so without wasting too much of time, I am going to start the polymerization, types of the polymerization. You can see here the heading is types of the polymerization. So basically we have the addition polymerization and the condensation polymerization. And in today's class, I am going to discuss only the addition polymerization in the pretty much detail. And you should know the one thing, the other name of the addition polymerization is the chain polymerization. Okay, so whether you call it as the addition polymerization and the chain polymerization, both are same. Right. So if you don't know what is the meaning of the chain and what is the meaning of the step growth polymerization, don't worry about that. After the completion of the addition polymerization as well as the condensation polymerization, I will also explain the difference between them in the pretty much detail as well. Okay. So what actually we do in the addition polymerization, you can see in addition polymerization, entire monomers are linked together to form a long chain polymer. That means you have been, say for example, you have been given the large number of the monomers. So all these monomers will merge together or the link together to form a macromolecule, and that molecule would be your polymer, right? So this is just one example, CH2 double bond CH, and this is the SG. SG is the substituted group. That means you can substitute this. Earlier you are having the hydrogen here, right? But I have substituted that hydrogen with the SG group, and if you put H instead of this hydrogen, then you will get polythene, as I have explained here, substituted group. If you put H in place of the SG, then you will have the polythene polymer. And then if you put the CH3 instead of the SG, then you will have the polypropylene. If you put chlorine in place of the SG, then you will have the polyvinyl chloride. If you put phenyl group in place of this, then you will have the PS, which is your polystyrene. If you put cyanide here, then it would be polyacrylonitrile and many more. So basically, this thing is basically the polymers which belongs to the vinyl class. So these all are the vinyl polymers basically, whether you call it as polypropylene, polyvinyl chloride, polystyrene, polyacrylonitrile, polyacetate, many things, right? They all belongs to this particular class, which is the vinyl class of the polymer. I hope this is quite well understood now. And then now moving to the next page. Okay, the addition polymerization. See, addition polymerization is a chain reaction. So it is a type of the chain reaction, and if you can recall your very basic reaction of class 9th, where you have already learned the concept of the free radical substitution reaction, where you have the different steps, right? Chain initiation, right? And then propagation and then termination. So all these three steps are also going to be here in this case also. So basically it is addition polymerization, which is a chain reaction, and this consists of the three steps. First is the chain initiation step for the formation of the active centers. It is very, very important to note that whenever you have the active centers, only then you will be able to produce a polymer, right? So it is a general way. In the upcoming slide, I will also explain with the help of the example, right? Say you have this species, which is a neutral species, and it goes the under initiation with in presence of certain solvents or say light or some other thing. It will produce some active species, and basically this is your initiator. This is initiator radical. And what happens? This initiator radical then attack your monomer, okay? And then the chain propagates. Propagation means the increase in the length of the chain to the desired value of degree of polymerization. Okay. So A, then A, and this process then gets continued. Like this is another active species now, right? And that active species, because it is having the odd electron, it will attack on the monomer and it will produce next species. And this process keeps on continuing up to the extent of getting your desired molecular weight of the polymer. Once you have the desired molecular weight of this active species, then you have to terminate this chain reaction, this chain propagation reaction. So your third step is the chain termination, which is basically the removal of the active centers. So here we will remove this active center from the molecule, right? This electron from here, and you will have this dead species, long chain, or you can say the high molecular weight dead species, and this dead species is basically a polymer. So this is the pretty much straightforward concept actually, right? So here free radical mechanism you will have on the basis of the, see, when you are discussing this addition polymerization, if you can recall your reactions of the alkenes, then in alkenes also you may have your free radical addition reaction, then your electrophilic addition reactions, right? Various reactions are there. So here also you are having the free radical mechanism for this addition reaction, and then ionic mechanism, that is anionic and cationic. Both anionic mechanism and cationic mechanism would be there. And after that, if you go for the Ziegler-Natta catalysis and all these things, then coordination polymerization is also there in case of the addition polymerization. But right now I am discussing only these two. First free radical and then ionic. And in the ionic, I will discuss anionic and cationic, right? So what happens actually, you see, this is just one example. So what we are doing here, we are taking some initiator molecule basically. It is the initiator molecule, and you can see this is oxygen, this is another oxygen. So this linkage is the peroxide linkage. So this initiator is basically a peroxide. So organic peroxides are used as a free radical initiators. This I have written here. So this organic peroxide will undergo the homolytic fission under the given conditions for the polymerization, and it will break like that. See this bond, this covalent bond is nothing but it is a pair of electrons. So this goes the homolysis or the homolytic fission. This undergoes the homolytic fissions, and one of the electron will move onto this particular oxygen atom, and your next electron will move on this particular oxygen atom. So you can see here half-headed arrow I have shown here, and in the general organic chemistry, half-headed arrow represents the movement of the one odd electron. So this bond then breaks from here, and you will get the two organic peroxide free radicals. These are the these two are the free radicals, and these are basically the initiator radicals. And in place of the R, if you put CH3, then it is your alkyl radical. If you put phenyl or the benzene ring, then this is your phenyl substituted radical species. So R could be anything, your CH3 or your CH3 or your C6H5, or you can take any other substituent also. Okay, now this radical you have produced, then what happens actually in that case, you see this will produce the another active species and will remove the carbon dioxide from here. So how we can remove the carbon dioxide? This bond which is present between the carbon and this alkyl group, whether it is phenyl or methyl, it will not make any difference. This will again undergo the homolytic fission. One of the electron of this pair will go to this, will go to here in this particular position where you have carbon and oxygen single bond, and one of the electron will move to the alkyl group, and one electron is already present here on this particular oxygen atom. So one electron from this bond, one is coming from this bond. So this will make a double bond, and this carbon double bond carbon, you will have the carbon dioxide. This you will eliminate from here, and this is your simple free radical which will start your polymerization reaction. So here you can see this radical species, this is attacking on my monomer. So I have substituted with this X here, but in case of the X, you can write SG also, as I have explained in my last slide, or you can straightforward say in your example, you may have the question like this. Explain the addition, free radical addition polymerization of the polyvinyl chloride. So you will put CN here, right? If the question is like that, explain the addition polymerization of polyhydronitrile, then you will put CN here. Otherwise, in generalization, you can put X here or the SG here, right? So what will happen in that case, you can see here, this is the double bond. Under the influence of this radical species, this will again undergo the homolytic cleavage, and one of the electron will shift onto this carbon atom, and one of the electron will shift onto this right-handed carbon atom, which is containing the substituted group, right? And then you can see here, this is having your odd electron now, and this one electron actually will go here, right? So here you are having two species, your secondary radical and your primary radical. So how I am producing primary and secondary radical, this is quite simple. Say this is the path one. This this R is attacking onto this one, and one electron is coming from here. That means the bond between carbon and this alkyl group will form, which is this carbon which is bearing the CH2 ions. This will connect with that. So this is the first case actually. This is connecting here, and one will shift here, right? And this will have your odd electron. So this is your secondary radical, and you know the second radical is more stable, right? Because this carbon is the secondary carbon. So this is the first pathway which is producing this particular species, right? And in the second state, what can happen? Instead of attacking onto this particular carbon atom, this radical species will attack onto this carbon. That means this carbon now, which is having the substituent, this will also have the R, and this species will have the odd electron in the second state, right? So here you can see this R gets corrected here by this linkage, and one electron actually is moving from here, and this is having one electron. But this radical, you see, this carbon is the primary carbon. So this radical is the primary radical, and it is the minor one, but both will form, and this will form in the major amount. So major part in the polymer will be this type of the reactive intermediate, which will give the chromatic, right? I hope this first step, which is the chain initiation step, is quite clear now, okay? And now the chain propagation step. Now your chain will start to propagate. That means generated free radicals, which I have produced in the last slide, attack another molecule of monomers and continue the process to form a desired long chain. Desired long chain means whatever the molecular weight of polymer you require, you can go up to that extent, okay? So here this radical I have produced in my last slide here. If I go back, you see, I'm starting with the secondary radical because it is more stable, okay? But this will also form the product, please remember, okay? So this radical now will attack on the fresh molecule of the monomer. This is monomer molecule, right? And this will attack onto this one because this is the secondary pathway. So I'm attacking this from here actually, right? And one electron after the cleavage, homolytic cleavage of this double bond, this will come here, this will go there. That means this now connect with this one, and your odd electron will be here. This will produce your species, right? You see R, which is this one, CH2, CHX, R, CH2, CH2X. This gets connected with the CH2. This is CH2, and this will become now the single bond. This is single, and this is the odd electron here. This is X, right? So here you can see I have shown you 1, 2, 3, 4, 5 arrows, right? So these 5 arrows means that means the reaction is going on, right? This reaction is going, this propagation step, this going on up to the formation of the desired molecular weight polymer, right? Or that means the desired chain length. Once you have the sufficient high molecular weight desired this active radical, then you have to terminate the step to get the dead polymer. Okay, so what we do in the termination step, in this step, that means in the termination step, chain of the desired length or the desired molecular weight terminate to give the polymer. Okay, dead polymer. And this termination basically involves any of the three methods, right? This termination can occur by the coupling reaction. That means these two such species will couple to produce the dead polymer, or disproportionation reaction may also occur in that case. I hope you know what is the disproportionation reaction, okay? And third is the chain transfer reaction. So we'll see all the three methods to produce the dead polymers, and all these three methods will occur in the system. Please remember. Okay. So first step is basically here. Okay, this is the same slide I have repeated. Okay, forget about this. Now this is the termination step, and my first termination method is the coupling method or the coupling reaction. So these were the growing radicals, right? So these, now I have put it N here, right? N means the degree of the polymerization. That means this will have the number actually, right? 10 raised the power 3 to 10 raised the power 7 up to anywhere, right? It may 1,000, it may be 10,000, 1 lakh, 10 lakh, right? And say more than 10 lakh, right? This you can exceed, right? So up to the desired chain length. So if I go back, right? So this is going on continuing. This reaction goes on continuing, and this will produce your this growing radicals, right? And I put it here, which is a very large number, and this is another growing radical, right? Chain, and this is again you see this one, N is here. So one electron from this species and another electron will from this species, they will get connected from. Okay. So there would be a new bond formation between these two, CHX and CHX, and this bond is this one, CHX, newly formed bond. So this is N, and this N is very, very high number, and by this you may have the dead polymer, which you can mold, or which you can process further to get ready for this polymer for the different applications. So this is one way, coupling reaction. Simply your coupling reaction is happening from here. Now there occurs the disproportionation reaction, and I hope you know what is the disproportionation reaction. I hope I think there is a spelling mistake. Please correct it. Please correct it. Transfer of hydrogen atom from one growing chain to another, which gives two dead chains. So in this particular disproportionation reaction, what will happen? One growing chain will transfer one of the hydrogen to the another growing chain, and by this method you have the two dead polymers. Of course, the species or the growing chain which will lose hydrogen, this will produce the unsaturated system, that is a double bond, and the chain which gets the hydrogen atom, it will produce the saturated part. Okay, so here you can see I have shown you the reaction. This is the growing chain, this is another growing chain, and hydrogen transfer is taking place. So this hydrogen which is present here in this CH2, so this bond will now cleave. One of the electron will go to this hydrogen atom, and one active electron will grab this hydrogen radical, and this will put CH2 here, right? So this will put CH2 here. So here you can see CH2X, and this is the saturated part, because it is getting hydrogen. And second part, what will happen in the second step? What will happen? See, this hydrogen is removed from here, but one electron we left here, so electron will come here, and this electron will go there like that, and this will form a double bond. And where first the double bond is formed here, so this is where you see CHX double bond CH, CHX double bond CH. This is the unsaturated part. So this is polymer part, this is another polymer part. But you may have some confusion. See, this is basically CH double bond CH. This is another active part. Basically, this is the end group, and there are lots of methods to utilize this active end group in order to get the dead polymer. Right. So don't worry about this. Your end part, right? Your end group, right? This will not make this will not make any difference in the properties of the polymer, because we have the method to eliminate this as well, right? Now, okay. So my third method is the chain transfer reaction. So what will happen in the chain transfer reaction? You can see here. Basically, this chain transfer process or reaction takes place with the abstraction of one hydrogen or some other atom, either from the monomer or from the solvent or from the impurities present in the system. And in this method, basically the deactivation of the chain results in the formation of a new radical. And this new radical can initiate the fresh polymer chain reaction. But if you want to stop it, then you can eliminate or utilize that active radicals also, right? So This is very important in order to take this chain transfer reaction. Your solvent, right, or any other impurity or monomer will play the very important part. So this is your again growing chain polymer, and say this is your RH. This is say for example, say this is some impurity or the solvent, right, which is carrying a hydrogen from here. So this bond undergoes the cleavage and this will shift here, okay, and this electron will grab this hydrogen atom along with this one electron, and this will now become CH2, right? So this you will have dead polymer or your long chain polymer, and this is your active radical, right? This is your active radical. If you want, then you can utilize it, or it may start the fresh reaction if you want to proceed the reaction further after the removal of this dead polymer, right? Now, this is the example of your free radical addition polymerization, right? Simple, this is your chain transfer reaction. And with this, your free radical mechanism, how many kinds or what kinds of the different polymers we can synthesize? PE, that means polythene we can synthesize with this reaction. LDPE, low density polyethylene. HDPE, high density polyethylene. And your tetrafluoroethylene, which is your Teflon, very famous polymer, right? All these species are the few examples which are synthesized by the free radical addition polymerization, and this is very important for your assignment part. See, in your assignment, I may ask the question like that. See, I may give you the example, some few of the examples, and can ask you to select the species which are formed by the free radical polymerization, which are formed by the radical anionic polymerization, right? All these things, right? This stuff is very important for your assignment part. Okay. Now moving to the next. Now the next, see, I have completed the free radical chain polymerization, free radical addition polymerization. Now I am going to discuss this cationic addition polymerization. Free radical mechanism is also there, but cationic mechanism is also there. But there would be some conditions which are essential or must in order to proceed the reaction through this cationic addition mechanism, right? So what are these important conditions? Number one, presence of acids. Like you may have your sulfuric acid, you may have your hydrofluoric acid, and you may also have your Lewis acid, right? SnCl2. Sorry, this is not S capital N, this is small n, right? Please correct it. This is SnCl4, stannoctane, right? Right? And this is your BF3. All these are the Lewis acids. So along with the Lewis acid, you may also have the protic acid, right? Right? Or you may have the some other traces, right? You may also have the some other traces of the water, which are very important, right? And then your electron releasing alkenes, or basically the alkenes, whatever alkenes you are having, they must be the electron releasing group, right? For your cationic addition polymerization, cat I have written there for this. Okay, so your alkene must have the electron releasing group. That means plus inductive effect showing groups, right? In order to get your this particular mechanism. So example is what? Isobutylene, right? I am taking the polymerization of the isobutylene, which will give you the polyisobutylene polymer, right? So here you see this is CH2 double bond CH, and both of the hydrogen of the alkene I have substituted with the alkyl groups, that two methyl groups with the two methyl groups CH3 and CH3, right? So this is isobutylene, and you know this is electron releasing group. This is also electron releasing group. That means this will push the electron density towards this particular system, and electron density on this particular carbon atom will be very high. And if you subject this isobutylene to this polymerization, you will get the polyisobutylene, right? So how the mechanism goes? Again, the same thing. Your chain initiation step would be there. So they say I have taken this BF3, your Lewis acid, right? Because it is electron deficient compound, it can accept the species which are having the electrons, right? So here this is your water which is present in the system, right? So H positive, OH negative I have written here. Since this boron can accept the electron pair, so this OH negative will shift onto this boron, and you will have this particular compound, addition compound, BF3OH negative, and this is the cationic part, which is your H positive, and this, because the mechanism is the cationic addition polymerization, so this H positive now will start the reaction. So this is your isobutylene monomer, And this is your species which I have produced by the reaction of BF3 with the water. And you know, so this having the electron density from air. So what can happen in that case? Say for example, electron pair are shifting here, just like that. Okay, electron pair are shifting here. So what I can do, I can show you. Say this electron pair is shifted here, like that. Okay, so this electron pair will get this hydrogen. So this will become CH3. Okay, you can see this is your CH3. This will become single, and of course the positive part would be there because this carbon has lost the electron pair. Okay, and BF3OH negative, the counter ion would also be present here, right? So this reaction goes in that manner. Fine. Now you have this particular species. I can rewrite this species in the propagation step like that. This is CH3, CH3, C positive CH3 because this carbon is having the 3 ethyl group, and this is positive, and in the bracket I have quoted this BF3OH negative, right? So counter ion will always be there. And now this is your fresh monomer, fresh isobutadiene, and n molecules I have taken here, which may vary from 10 to the power 3 to 10 to the power 7, right, or any other number, depending upon the desired molecular weight of the polymer. Okay. Now what will happen? You see, this reaction when goes again and again, right? See, this is your what? Positive part. Okay. And this when your negative part. So what can happen in the next step? This can come here. Okay. In the one instant, and this can go there as well, right? So this will attack. Now this, because this carbon is carrying the negative charge, this will attack onto this particular carbon atom, right? And the chain will form with this carbon and this CH2 group, and this will get the negative part. Okay. So how the reaction goes, you see, there's a CH3, CH3, CH3C like that, and this gets connected with the CH2. So this is your CH2. This carbon is already here, which is this one, right? And CH3, CH3. Because I have taken the n numbers of the molecule, so this reaction goes on n times. I can show you, right? Here you see, this is n minus 1, right? And this is where CH2, and that part goes, this reaction continues up to the extent of your desired molecular weight, right? And BF3OH negative like that you are having. But do not confuse into this n minus 1. N minus 1 means the length of this particular chain will be having one carbon or less than this particular unit. But the removal or the addition of the 30 such unit, 30 to 40 such units, right, will not make any difference in the properties of the polymer. So basically this n minus 1 is of no practical use, but it is only showing that the chain will have the one monomer less than this particular, then the number of the monomers you have taken, right? So this chain is propagating like that, right? And you are having this species which is in the ionic form, it is active again. So in the next step, what you can see, you can go for the chain termination step for this species. Chain termination occurs when the collision between the two growing C positive ions takes place, C positive ion and the anion takes place, right? So that means one anion and one C positive ion. If the collision will occur between the two, then the termination would occur. And of course, there are two possible ways for this particular termination to take place. First way is the loss of the hydrogen ion from the growing chain to the counter ion. Counter ion means the other anion which is present here, right? Resulting in the formation of a double bond at the end of the growing polymer molecule. Say this is your active part, right? And you see this is growing chain. One of the hydrogen from this chain will lost to the counter ion. This is positive, this is the counter ion. So this negative part, this negative charge, this electron pair will grab the hydrogen from here. And of course, this electron pair will come down here. So this will get doubled down, right? Neutral species. And this we have removed from here. So this is your species, which is the unsaturated part. This is the BF3, which is here actually. OH negative will combine with the H to give you the H2O. Again, you will think that, okay, this is again, you see the isobutadiene part type. This is the active part. This the reaction may go further. But remember, this is the end group. And we have ways, we have the various ways to and this to remove this end group or to neutralize this end group in order to get the polymers. But up to in this particular lecture, there is no need to discuss how we can remove this end group. Okay. And the second way, formation of the covalent bond between the carbonium ion, that means this positive charge, and the counter ion, that means this one, when the termination occurs by simple coupling, that means these two can couple also. So last is your chain termination by simple coupling, right? So this is your H positive, this is your BF3OH negative. So this negative will go here actually, and this will join this negative part will join to this carbon atom, which is positively charged, and you will have this COH, right? So BF3 will remove from here, and again we have the ways to neutralize this OH as well, and you will get the polymer. So this is the cationic mechanism. The important conditions, the your acids must be there, and your electron pushing groups are there. So when I discuss the anionic mechanism, the reverse condition will be required. Okay, let's see what are the next conditions. So here you can see the anionic addition polymerization condition required. Presence of alkali. In the earlier case, in the cationic mechanism, the reaction demands the presence of your acids. But here the alkali or the alkali metals like sodium, potassiums, or the Grignard reagents of the alkali metals or sodamide, various things are there, right? These are the conditions. Second, electron attracting alkenes must be there. Electron attracting means electron withdrawing group. Minus I effect must be there. Minus I effect showing groups must be there, substituted onto the alkene. So this is where say CH2 double bond CH. Here this is Cl, right? The Cl is having the both effects, electron pushing as well as the electron attracting. But since it's electron attracting group, that means minus I effect is more predominating. So polyvinyl chloride, if you want to synthesize the polyvinyl chloride, then you can go for the anionic addition polymerization. Again, this is very, very important for your assignment part. So you have taken the n such molecules, very high number, 10 to the power 3 to the 7, as I have explained, and when you subjected this into the polymerization, of course the condition would be there, which I have got written here, and you will get your polymer. So how the mechanism goes? Again, the chain initiation step is there. This is your NH2, which is the amide group, which I have extracted from this sodamide, right? NH2 negative. And this Cl is electron pushing, making these hydrogens. This bond between the carbon and hydrogen is weaker. That means it is these hydrogens are a little bit acidic now. Okay. So this NH2 negative can grab the hydrogen from here, and or it can attack. No, it is not removing the hydrogen from here. I'm sorry. Okay. What can happen? This NH2, right? This is electron withdrawing, right? So it will withdraw the electron density from here, making this carbon electron deficient, right? So of course your electron-rich species will add to this, and your NH2, CH2, C double bond, and one negative is here, and counter ion sodium would always be there. This is a secondary carbocation, right? This is a secondary carbocation. Otherwise, this NH2 negative can also attack here, but this will produce the primary carbocation, which is less stable. So I haven't shown that particular thing here, but in your assignment I may ask that question also. What other possible way of the formation of the carbocation in that case, right? This may I have this I may ask in your assignments as well. Okay. Now once the initiation occurs, then the propagation will start. Your NH2 CH2 CH negative Cl, and this negative part will attack on the fresh vinyl chloride molecule, the fresh monomer, and this will get links from here, and this will get the negative, and this process continues n times in order to get the desired molecular weight polymer, and you will have this negatively charged species, right? N-1 of course is there. Okay, one monomer will be less in that case again. Okay, but don't worry about that. It is not so very, very important, but I'll discuss this thing in the separate lecture, why this happens actually. Okay, but right now you can understand this in that manner. Okay, and please remember, removal of the 30, 40 or 50 units or the 50 such units from the polymer will not actually affect removal or the addition of this 30, 40, 50 units will not affect the properties of the polymer. So there is actually no importance of this -1 here. Practically I am saying, okay. And then the chain termination will occur, and in this chain termination, this will present in place of the H positive, which comes from the solvents or say from other acids, right? So H positive is there, this negative will grab this one, you will end up with this polymer, okay? So basically this is your polymer, this is the end group, okay? We are having the ways to remove this, right? And as well as to remove this, but the properties of the molecular, this polymer actually depend on this part actually, right? And that part is not affecting this end groups are not affecting the properties of the polymers much. So you always focus on this particular part, right? So this is the addition polymerization, right? And I have discussed the three different pathways. On the next class, I'll discuss the condensation polymerization. Okay, if you like the video, please press the thumb button to like my video and to share the video with your friends also. And if you are new here watching the video for the first time, please subscribe the tetrahedral chemistry classes. Okay, thank you. Bye bye.